Hi class, today we're going to talk about capacitance. Now, like resistance, capacitance is a property of an object. It characterizes how much charge will be present given a certain voltage. So everything can have capacitance. The more charge you can hold given a certain voltage, the more capacitance you will have. The formula for capacitance is very simple. It's given by C equals Q over V, where C here is not coulombs, but capacitance, and Q is the charge, and V is the voltage. The units for capacitance will then be coulomb over volt, or it's also called the farad, F, named after Michael Faraday, who did a lot of experiments with capacitance. Now, the last thing we need to know about capacitance is that it only depends on the geometry, the size and shape, and the material present. It doesn't depend on anything else. For example, it doesn't depend on the voltage. So now we can go ahead and calculate capacitance for various objects. For instance, the charged sphere, the parallel plate capacitor, and each one will have a unique expression for its capacitance. So let's start with the charged sphere. Here we have a sphere of radius r, for which we charge it uniformly with a charge q. Now we know the surface of this sphere is going to be at some voltage V, and we can calculate this voltage because it has the same expression as for a point particle when the radius is much greater than r. Namely, at the surface, the voltage V is going to be equal to kq over r, the radius of the sphere. So its capacitance, C equals Q over V, is simply going to be Q over the voltage V, Q over kq over r. And then we get the capacitance is equal to the radius of the sphere r over k. So you notice now that the capacitance only depends on the radius. So the bigger the sphere is, the more charge it can hold. So, for example, given a sphere with a radius of 1 meter, the amount of capacitance would be 0.1 nanofarads. Now let's look at parallel plates. Here we have two plates separated by a distance d, and we put charges plus sigma on the bottom plate and minus sigma on the top plate. Here sigma is the surface charge density, Q over A. Now we've derived the electric field for this before. Outside the plates it's 0, but inside it's constant and given by E equals sigma over epsilon naught. We also derive the potential difference across these plates as being simply V equals ED. So putting in for E, we have this, and putting in for sigma, we have this, and finally, this reduces to QD over A epsilon naught. To find capacitance, which is simply C equals Q over V, we just put in for V what we found above. And this reduces to a very simple expression. The capacitance is A, the area, times epsilon naught over D. So if you make the plates bigger, wider, the capacitance increases. It will also increase if you decrease the separation between the plates. So, for example, if we have a pair of plates 10 centimeters by 10 centimeters and separated by 1 millimeter, the capacitance would be, again, 0.1 nanofarads. So let's go from talking about capacitance to talking about a capacitor, which is nothing more than a component in an electronic circuit, a very essential component. So whereas a resistor is used to slow current, a capacitor is used to store charge so that we can use it later in the circuit. The symbol for a capacitor in a circuit is given here. It looks like two parallel plates, and capacitors have values that range anywhere from 1 millifarad all the way down to 1 picofarad. Now, one type of capacitor that everybody's familiar with, but it goes by another name, is a battery, which is just one big capacitor because it stores a lot of charge. So, for example, a typical AA battery, which is at 1.5 volts, has a capacitance of about 1 farad. Now, the symbol for the battery is slightly different. It looks like two parallel plates like a capacitor, but one is drawn wider than the other, and sometimes there's a plus sign to indicate the polarity, showing which side should be positive voltage. So let's look at a simple capacitor circuit composed of a battery at voltage V0, a capacitor C, and there's a switch which we can use to turn the circuit on and off. This symbol down here means ground. If we don't have it, then the circuit can be floating. This point right here won't be 0 volts, but with this symbol it means it's going to be 0 volts relative to the Earth's ground. And we'll talk about that a little bit more later. So what happens when the switch is open? Well, when the switch is open, no current flows, and positive charges and negative charges here. The positive charges want to get away from each other. They want to go away. They can't cross this gap. There's a gap between plus and minus. So they're stuck there. On the capacitor, there's no charges on it, so there's going to be no electric field and no potential. Now, as soon as we close the switch, the positive charges want to get away from each other, so they will start flowing and deposit themselves over here. The negative charges also want to get away from each other, and they're also attracted to the positive charges, so they will end up here. So we will have positive charges on one side of the capacitor and an equal amount of negative charges on the other side. The electric field will no longer be 0, the voltage will be the same voltage as the battery, and the charge will be given by the capacitance equation, the capacitance times the voltage of the battery. So let's look at what happens when you put capacitors in parallel. What we mean is, if we have a circuit where we have two capacitors, C1 and C2, and we put them such that they see the same voltage from the battery, V. They will have different charges because the capacitances are different. So C1 will have charge Q1 and C2 have charge Q2. So what we want to know is, can this circuit be replaced by a different circuit, an equivalent circuit, where there's only one capacitor, CEQ, EQ for equivalent, and charge Q and minus Q, yet behaves exactly the same as the two capacitors that we have over here. What we would like to know is, how can we write an expression for C equivalent in terms of the original capacitances, C1 and C2? Well, we can use the capacitance equation to write down the charges for Q1 and Q2 and the charge Q on this circuit. So we see something interesting. They all share the same voltage, V, but they all have different charges, Q1, Q2, and Q, which brings us to a general statement that capacitors in parallel have the same voltage but different charges. Now, from the point of view of the battery, it doesn't know how many capacitors are connected to it. It just knows that there was a certain number of charges that flowed out, namely Q1 plus Q2, and a certain number of charges that flowed out here. And if it's truly equivalent, those charges must be the same. So explicitly, Q must equal Q1 plus Q2. Putting in our expressions for the Q's from above, we have this. And then dividing out V, we're left with C equivalent is equal to C1 plus C2. And so the general rule is that when you have capacitors in parallel, the capacitances just simply add. So let's look at capacitors in series. Here we have a circuit that looks like this. Now you have two capacitors arranged so that one occurs right after the other. When they're connected to the battery, charges will flow from the battery over to capacitance C1 plus Q on this side. On the other side, an equal but opposite charge will accumulate minus Q, and to conserve charge, there should be positive Q on C2 this side, and likewise, an opposite amount of charge minus Q will accumulate on the other side of C2. So we have the same charges, but the different across each capacitance, there will be different voltages for the same charge accumulation. Thus, we come up with the rule for capacitors in series is that you have same charge but different voltages. So the question now is, can we replace this circuit with an equivalent circuit with one capacitance, CEQ, and what would that capacitance be? Well, using the capacitance equation again, we can write down the values for V1, V2, and V written here. Now we notice one thing is that the voltage drop V1 and V2 must equal V when you add them together. In other words, V must equal V1 plus V2. So putting in our expressions for V's, we get, and dividing out the Q's, we arrive at 1 over CEQ equals 1 over C1 plus 1 over C2. Thus you get the rule for capacitors in series. The reciprocal of the equivalent capacitances is equal to the sum of the reciprocals of each capacitance. So let's do an example problem. Here we have three capacitors. Two of them are in series, and these two in series are in parallel with a third capacitor, C3. So the first thing we want to do is reduce these two capacitors, C1 and C2, into an equivalent capacitance, C12, where the circuit would now look like this. Because C1 and C2 are in series, we have to add their reciprocals. 1 over C12 equals 1 over C1 plus 1 over C2. And if we put in the numbers, we'll get this, which reduces to C12 equals 10/3 microfarads. Now we want to add C12 and C3, which are in parallel, to get another equivalent circuit, namely C123, which is which will be the equivalent capacitance of the entire circuit. Of course, since C12 and C3 are in parallel, their equivalent capacitance simply adds, and it is C12 plus C3, and putting in the numbers, we finally get a value of 22 over 3 microfarads. Okay, that's it for today. Bye.